On example 3, we want to estimate the area of region S bounded by the graph of y equals x squared, just a regular little parabola, parent function, the x-axis and the lines x equals 0 and x equals 1, as we can see here in this picture. And you can see it kind of almost looks a bit like a triangle, but most triangles that I am aware of don't have this nice curved surface right here. Okay, so it's not like there's a geometric formula that we could use and we could just plug our, say, our length, our base, and our height in, and we can find the area underneath the curve. Instead, what we need to do is we're going to first approximate it. We're going to approximate it by breaking it up into geometric shapes that we know the area for, like squares, rectangles, things like that. So our first approximation could be just a square. I can surround this whole entire region with a square whose side length is just 1 unit. It would look sort of like this. Okay, so you find the area of that. It's 1 times 1. It's 1 square unit, right? And just looking at that as an approximation, it's obvious that that is an over approximation. And we know that the area has to be less than 1, but at least we have a place to start, right? Now, a thing that I can see from this is that the base length here is the width of the interval, and the height is a function value. Like the height hits right there on the parabola at 1, 1. Okay, so that's going to come into play whenever we try to refine this as a method, breaking this into smaller and smaller pieces. Okay, so how can we find a better approximation? Why not break it up into, I don't know, let's say 4 pieces instead of just 1? We could do 2 pieces, but hey, let's go ahead and skip to 4. Okay. All right, so here is that division. We're going to take the region down here at the bottom, which is just a width of 1, and we're going to break it up into 4 smaller regions. And those small regions, that's called a partition. Whenever I take my interval, whatever it is, and we break it up into subintervals, that's called a partition. And this one specifically gives us 4 subintervals. How big is each one? Well, the whole entire thing is 1. I break it up into 4 pieces, so 1 divided by 4. Obviously, they should be 1/4 unit each. Okay? So, now, I don't actually have like geometric shapes just yet. Still, I mean, sure, it's a geometric shape, but it's not one that we have a formula for. You can see it kind of looks like a little trapezoid here. As a matter of fact, that's one of the ways that we approximate the area underneath the curve, but we're going to start with some rectangles. And I don't have rectangles just yet, but I'm going to get there, okay? So to define some rectangles, basically what we're going to do is so we're going to use, just like the previous example, we're going to have to use one of the endpoints as the height of the rectangle. And for each one of these little sub-regions, these little subintervals, I can either use the right side to make a rectangle, or I can use the left side to make a rectangle. We're actually going to do both of them. Let's start with the right-hand side. We're going to call this one a right Riemann sum, as you're about to see. Okay, let's come over here. And using this little partition, I'm just going to use the right endpoints as the height of my rectangle. For example, I bring this one straight over and come straight down. There's my first rectangle using this right endpoint on S3, right endpoint on S2, and the right endpoint on S1. Okay, so here then are all my rectangles. So to find the area underneath the curve, I can just add up each one of these rectangles. It's not going to be perfect, but it's definitely going to be better than that first approximation using 1 square. Okay, so whenever you go to find the area of a rectangle, we know its area is equal to a base times a height. So our base length is basically these lengths right down here. It's the width of each one of these rectangles. And the width of that rectangle, in this case, is 4. We're going to call that thing, the width, we're going to call it delta x. And in general, if they are all exactly the same, you take the width of your whole entire interval, in this case 1, and you divide it by however many subintervals that you want, in this case 4. So obviously the width of each one of these rectangles is 4. All right, the other thing that we need is a height. And the height is going to be a function value. What we do basically is we take the x value, in this case the 1/4, and we plug it into the function in order to find the height of that first rectangle. So the first rectangle's height would be f of 1/4. The height of the second rectangle, I would take the 1/2 and I would plug it into the function. F of 1/2, f of 3/4, and then f of 1, or if you want, 4/4. Okay? So if we just multiply these things together and then add them together, we have the area underneath the curve. Okay, so I'm going to systematically do this because it's going to pay off in the end whenever we talk about how to do it in more complicated situations, and especially situations when instead of having 4 subintervals down here, we have a generic n subintervals. Okay, so here I'm going to write the area. That's not how you spell that word. Area as approximately equal to a sum from I equals 1 to 4 of, I'm going to have some sort of function here that I'm going to multiply times the width. This function value here is going to be the height of each one of the rectangles, and this should be the width. Our width, well, we already know that that's 1/4 for each one of these rectangles. Now inside here, I'm supposed to have 1/4, 1/2, 3/4, and 4/4, where this one is from I is equal to 1. This one is from I is equal to 2, I is equal to 3, and I is equal to 4. So if we were going to generalize it, can you see that this one is just I is equal to 1/4, I is equal to 2/4, so 2/4 would reduce to 1/2, I is equal to 3/4, and so on. And so in general, it is, take out this question mark and put I/4. And remember when we were talking about that summation notation, you would start with this 1 and you'd plug the 1 in and evaluate it, plus then you increase by the next integer, you'd stick in 2 into that function, and so on until you get to 4. So the answer to this would be equal to f of 1/4 times 1/4, the width, plus f of, we'd increase the counter by 1, it'd be 2/4 times 1/4, plus, running out of room, so I'm going to continue on the next line, f of 3/4 times 1/4, and then finally 4/4 times 1/4. Okay, now as far as adding all of these things up, it's pretty much you throw that thing into a calculator, right? So we have a function. That function is given to us as y is equal to x squared. You'd plug in 1/4 just as an example. You would take y of 1/4. You'd square that thing, so 1/4 squared is equal to 1/16. Okay, and then in order to find the actual area of that rectangle, you're going to multiply it times 1/4 for this part. So you'd have 1/16 times 1/4. You can see you definitely don't want to have to do all of this thing by hand. So there's the area of that first rectangle, and you do that for each one of them, add them all up, and get an approximate area of, and let me encourage you to do this on your own. We're going to say, no, actually, this is exactly equal. This is a rational number here. It's just a long decimal. It is 0.46875. Yeah, there you go. So there's approximately the area underneath the curve using this thing that we're going to call a right Riemann sum. So let me come back over here. We can take a look at each one of these. Ooh, so here is a nice diagram for each one of those rectangles. And we talked about the rectangle width as being this delta x thing. In this particular case, it is 1/4. So in this calculation here, the 1 is coming from the right endpoint, the 0 is coming from the left endpoint. You subtract those, that's where the 1/4 is coming from, of course. All right, and then the rectangle widths evaluated at each of the right endpoints, which is why it's called a right Riemann sum. And the reason why it's called a Riemann sum is because of that mathematician Riemann who came up with it. And think about the things that you are summing up. Yeah, it's rectangles, but in order to find the areas of each one of the rectangles, you're taking a function value and you're multiplying it times the width, that partition of your interval, and then adding up all of those things to get ourselves a right Riemann sum. But we don't have to just use the right side. We could have used the left side. We can see that this is too big. So in the next one, in the next instance of this, what we're going to do is we're going to look at it from the left-hand side. So if we use the left endpoints, this is what it's going to look like. And you can see that this one is going to be an under approximation. And this always happens whenever you have an increasing function. So let me go back to this example. We have an increasing function, and when you use a right endpoint in order to use the height for each of those rectangles, part of it's going to stick out and you're going to over approximate it. But with that same increasing function, if you use the left endpoints for each of these rectangles, you can see that the rectangles are underneath the curve and you're going to be under approximating. So we'll finish up this example in the next video.